This is lecture 16 of Data Science 100 and Data Science 200, and the topic is cross-validation and regularization. Now, this lecture has a large number of segments, so I wanted to give you a brief roadmap or overview of what you're going to learn in this lecture. So in section 16.1 through 16.4, we discussed the training and testing splitting of data and cross-validation. In 16.1, we discuss why we need to split our data into training and testing data sets and how cross-validation works. In sections 16.2 and 16.3, we create a training and testing split, and then we use that training data to fit a model, and then we evaluate that model using the testing data. In section 16.4, we implement cross-validation. Now, note that we're using the pipeline object in scikit-learn, and that's out of scope for you in this class. All you have to do is see how we're actually using that to construct our pipelines. In sections 16.5 and 16.6, we discuss regularization. And in 16.5, we show why we need to regularize and how penalties on the norm of our parameter vector help us accomplish this goal. In section 16.6, we explicitly list the model parameter when using the L2 penalty on our linear model. And this is called ridge regression. Now, there are also 3 supplementary videos that accompany this lecture. They don't introduce any new material, but they might be helpful in understanding the material that we're covering in this lecture. And because they're optional, they don't have accompanying quick checks with them. Now, in section 16.7 and 16.8, we implement ridge and lasso regression in a notebook. So these videos they'll basically explain to you how regularization and cross-validation are actually used in practice. Now again, we use pipeline, which is not in scope, so just watch how we're using it, but you don't actually have to understand how we're using pipeline. Section 16.9 is another supplementary video, and it was created by Paul Shao, who is a TA for this class in the spring of 2020. And he gives a great high-level overview of both the bias variance trade-off and also regularization. So now let's dive into cross-validation. So here is a plot of some data. We have the data points in purple, and there are only a few of those data points. And then we have models that we fit to those data points of increasing complexity. So we start with a simple linear model, that's the green line here. And then we introduce radial basis functions, that's the purple line here, is one that has 4 radial basis function features. The orange line is radial basis functions features combined with a linear model, so 4 features. And then the cyan line has a number of features that's equal to the size of the data set. And so we're able to get the model to pass through all of the points so that our loss would be 0. Now, we've always told you all along that our goal is minimizing loss. But really what we want is not to just fit the data, but we want to predict the future. So using a larger data set, our test data set, the red crosses, we can look at what is the difference between our training loss and our testing loss when we look at that larger data set. And what we're going to see is that while we're able to get our training data error loss down to 0, our test error is going to be fairly high because we end up overfitting on the data. And the cyan line is a perfect example of that, right? If we look at the graph on the right, we can see that our training loss is 0, right? Because our model passes through all of the points in our training data. But our test loss is very, very high. In fact, it's the highest of all of the models, right? And so what we're ending up doing is overfitting to the noise in our data rather than to the underlying structure of our data, right? So 2 takeaways that I want you to have here. The first is that training loss underestimates the real loss, right? And so it's going to be a lower bound for the loss that we might see when we look at our test data or real world data or a larger data set. The second is that as we go from the linear model to the more complex radial basis function models, we see higher test loss. So even though we're increasing the complexity of the model, our test loss is going up. So the takeaway for this class is that I want you to think about model complexity versus error and understand the trade-offs between model complexity and error. So error is just a placeholder for loss. We use them interchangeably. And complexity, I put in quotes because it could be a variety of different things. It could be, for example, the number of features. So if we look at training, we're always trying to drive down our loss, our error, and that might cause us to create a model that is more complex, has more features. But when we actually look at the error or the loss that we have in test, we'll see that that might actually drop as we increase the complexity, but at some point, we're going to see this divergence where it starts to go back up. Right? And so our sweet spot, our best fit for our model is not all the way to the right as we might think from looking at training error or training loss, but rather it's going to be a sweet spot for our testing error. Now what happens, the way we can interpret this cartoon figure is if we look to the left, we're underfitting, right? We're not taking into account the structure of the data. Whereas if we look to the right, we're overfitting. And so we're focusing on the noise in the data as opposed to the underlying structure. And so it's a balance between capturing the noisiness and complexity of our data and the structure of our data. Again, key takeaway is that our training error typically underestimates our test error. So we can generalize this and think about two types of data, training data and testing data. And this is really a concept from machine learning. So when we're doing learning, we do that using training data. We use that to fit our model. But when we want to evaluate, well, how well did we do in creating our model, we use our test data. So we can check the generalization of our model. What kind of error do we see when we look at the model in general? So here on the right, we take our data and we split it into a training portion of our data set and a testing portion of our data set. So two questions that should immediately come to mind. How do we split the data? And what are the relative sizes of our training data and our test data? So let's start with the first one. So how do we split it? Well, there could be many different ways that you split it. You could split it randomly. So just pick randomly to put data either into the training data set or the test data set. It could be temporally. So based on when the data was collected, you decide whether it goes into training or testing. This is very important if you're trying to predict something where things change over time. So I'll give you an example. If I was trying to predict whether a particular application binary was malicious or not, well, the kinds of techniques that hackers use to create those malicious binaries changes over time. So if I just randomly took a data set of, application binaries collected over time and randomly assigned them to training and testing, then I might actually train on binaries from the future and then test on binaries from the past. And as we all know, hindsight is 20/20. And so it would be cheating, and we would expect that actually our algorithm might not perform as well when it's exposed to things that it hasn't been able to see before, because it might not be generalizing on the right things. So that's an example of where temporality is actually very important. Another way we might split is by geographic region. So I might take a data set of US states data on something of interest and split it into regions. So maybe I train it on data from the West Coast states and test it on data from Midwestern states, and so on. But it's really going to depend on the application. Quite often it'll be random. But again, you want to make sure that you take any notion of temporality into account. Now, next question, what is the size of the training data set? What's the size of the testing data set? How do I determine that split? It might be, 90% training and 10% testing. Well, there's some trade-offs. If you have a larger training set, then we can build more complex models because we have more data to work with. But if we have a larger test set, then we get a better estimation of the generalization error that our model might have. So typically it'll be somewhere between 75% training, 25% testing, and 90% training and 10% testing. Now, very important is that you can only use the test data set once you've decided on the model. So we set aside that test data. We do all our fitting of our model only using the training data, and then we use the test data after we've shipped our model. Right? If we were to use the test data somehow like to try and get a better result out of training, then we would be cheating. Right? We would not be able to evaluate then using that test data because we would have contaminated the training process with test data. So you have to separate out that test data, only look at the training data while you're building your model and tuning your model, and then we can use the test data to evaluate it. Okay, so we take our data, we split it into a training set and a testing set. We build our model, and then we can evaluate it using the testing data. But there's kind of a question here, right? When I'm doing my training, I actually want to think about, well, how do I evaluate the model that I'm creating with training? Well, one way to do that is a validation split. So we're going to take our training data and we're going to split our training data into a validation data set, that's here in red with the V, and a training data set, right? So maybe we set aside 20% of our training data, again, completely separate from our test data. We set aside 20% of our training data as a validation set. Now we train our model using the training data, and then we can see how well did we do in training using the validation data set and use that to actually adjust the parameters of our model. Now we can take that process and repeat it multiple times. So that here we repeat it 5 times. So we take a different 20% sample each time and train 5 times. And so we can use that to tune our model. This is called 5-fold cross-validation. So cross-validation, what it does is it's going to simulate multiple training test splits on our training data. So it's the same thing that we want to do on the left with taking our data, training a model, and then testing it, but we're going to do it during the model training process. So let's go over a recipe for successful generalization. So the first thing you want to do is take your data and split it into a training set and a testing set. Typical split, 90% for training, 10% for testing. Put aside that test data set. We're only going to use the training data when we're designing, training, and tuning our model. Okay, we're going to use cross-validation to test the generalization of our model during this training phase. We're not going to look at the test data. Yet again, I'm going to say that. And once we've committed to our final model, we're going to train it once more using only the training data. And then we're going to test that final model using the test data. Now, if the accuracy is not acceptable, we have to go back to step 2. Right? And ideally what we're going to want to do is go out and get more test data. Because what it's telling us is when we trained, we didn't have enough data for our model. Perhaps that might have been one of the causes. We didn't have enough data for our model to be able to generalize. Now, once we're completely done, we fixed all of our model parameters, we train on all of the available data, and then we ship our model. And so this is the recipe for being able to successfully generalize on your data.